Hi guys, this is our last section of Chapter 7. So far we've talked about what is a sampling distribution, and we talked about sample proportions. Now we're talking about sample means. So by the end of this section, you should be able to find both the mean and the standard deviation of the sampling distribution of a sample mean, calculate probabilities involving a sample mean as long as the population is normal, explain how the shape of the sampling distribution of the sample mean is related to the shape of the population distribution, and then lastly, apply what's called the central limit theorem to help find probabilities involving a sample mean. Alright, so let's look at a couple things, and then we'll do some examples. So we reviewed our 10% condition, why we have to have a sample of no more than 10% the size of the population has to do with probabilities. We talked about the shape of our population distribution compared to the shape of a sampling distribution. Same thing with center and spread. We reviewed how to find probability if it's just taking a single item from your population. So in this case, we selected a young woman. We have our formulas, and then we talk some more about what those mean, making sure we're noting our notation there. We looked at finding examples of mean and standard deviation of our sampling distribution. So the mean of the sampling distribution of the sample mean is the same as the population mean. Note the notation there, please. Checking our 10% condition, right? That satisfies our independence one. And then we looked at some different distributions. And no matter the shape, we found that as long as we took samples of a certain size, it's going to be approximately normal or approximately symmetric. Mean, or the center is about the same in all of these. This is very important to know. I wouldn't say necessarily memorize it, but kind of understand why it works. So as long as your population is normal, it doesn't matter the sample size. We can assume that the sampling distribution will also be approximately normal. If we don't know it, or if we have a heavily skewed one, we have to take samples of at least 30. And then if it's only slightly skewed, samples of 15 or more are sufficient. Okay? So again, I'm reiterating a bunch here because I need you to know this. If the population is normal, then the sample distribution is normal. If the population is not normal, then as long as the sample is large enough, the distribution of sample means is approximately normal no matter the shape of the population. Okay? As long as it has a finite standard deviation. So the name of this is the central limit theorem. If it has a name, it means it's important. Central limit theorem says that when your sample size is large, at least 30, please remember 30, the sampling distribution of the sample mean is approximately normal. We care about this because we like it to be normal, so then we can use things like normal CDF to calculate probabilities. Okay, so let's look at an example. In this example, it's the same as we did before. The height of young women follows the normal distribution. But now, instead of picking a woman, we want to find the probability that the mean height of a simple random sample of 10 women exceeds 66.5 inches. So before we just looked at the chance that one woman was taller than 66.5 inches. Now I want to know what's the chance that if I were to take a sample of 10 women that their average is higher than 66.5. So let's go through our four-step process that we love so much. State, let x bar be the mean height of a simple random sample of 10 young women. We want to find the probability that their average is greater than 66.5. So let's come up with our plan. Since the population distribution is normal, the sampling distribution will follow a normal distribution. The sample standard deviation is given by this formula here. You do have to show your steps on how you calculated it. Now, it is safe to assume independence, since 10 women represents less than 10% of the population of all women. So once you've established that, go ahead and do your calculations. So I'm showing you two options for calculating. You can do the z-score method. Here's your x-bar. Here's your mean of your sampling distribution. Here's your standard deviation of your sampling distribution. Here's how we figure out that probability, right? You have to use your table. Or you can just choose to use your calculator and normal CDF, remembering to use your labels. Last step is to conclude. So there's only like a 0.5% chance of getting a sample of 10 women that has a mean height of 66.5 or more. This is really unlikely, right? Less than 1%. Not very likely to occur. Let's try one more example together. So this one's about servicing air conditioners. So based on many service records from the past year, the time and hours that a technician requires to complete preventative maintenance on an air conditioner follows the distribution that is strongly right skewed and whose most likely outcomes are close to 0. The mean time is 1 hour and the standard deviation is 1. Your company will service a simple random sample of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough time? What is the chance that the technician will not finish within the allotted time? So, what's the chance that he won't finish within the allotted time? So, let's go through. So, we should have a state. Let our x-bar be the average time that it takes. Okay. Our plan, our conditions. We have to check two conditions, independence and normal. Reasonable to assume that they've serviced more than 700 units. So 70 units in the sample does represent less than 10% of the population. So here's where that central limit theorem comes into play. Even though the population has a strong right skew, a sample size of 70 is large enough to assume normality. The mean of that sampling distribution is equal to the population mean, which is 1. Standard deviation of that sampling distribution is given by this formula. Comes to about 0.12. All right, let's do our math. So we have our curve here to represent, because we want to know what's the chance he doesn't do it within the time, aka what's the chance that the average is greater than 1.1 hours. So you can convert that to a z-score and do it with the chart, or you can just do normal CDF. This is a typo. This should be all zeros there. And then using our standard deviation that we found earlier. So that one was 0.12. If you want to be even more specific, you can do it further than that and get the about same response. In conclusion, as long as if you budget 1.1 hours per unit, there is a 20% chance that the technicians will not complete the work within the budgeted time. Okay, so take a moment, make sure you understand how we did this 4-step process, where these numbers came from, how we wrote this conclusion, what it all means. All right, another one. At the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. That information is important. Without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding that the contents weigh less than 16, or randomly selecting 10 jars and finding that the average weigh less than 16. What do you think is more likely without actually doing the math? Well, since averages are going to be less variable than individual measurements, you would expect the sample mean of 10 jars to be closer to the true mean. So it's more likely that a single jar would weigh less than 16 than for the average of 10 jars to be less than 16. So what I want you to do now is I want you to calculate the probability of each event described above. What's the chance you get 1 less than 16 ounces? What's the chance you get 10 with an average of less than 16 ounces? If you're not sure how to do this, look back at the examples we did about the female weights. It's the same steps. Remember, go through all your steps, 4-step process. The last example has to do with human pregnancies. Turns out that the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, average of 266 days, felt much longer than that, but I'll tell you what, and standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts more than 270 days. And then let's say...
Hello, good afternoon, everybody. This is Coretta.
Hang on. Sorry, I had to pause for the announcements. So, I think we left off. Suppose we choose a simple random sample of 6 pregnant women. Let X bar be the mean pregnancy length for the sample. Go ahead and figure out what is the mean of this distribution. Compute the standard deviation while checking the 10% condition. And then also find the probability that the average pregnancy length for the women in the sample exceeds 270 days. So, couple examples for you to work on yourselves and have ready for class the next time we get together. And then we have finished chapter 7. We'll have a test here in the next couple days. Lots of reviewing, all the fun things. Have a good one, guys.